Okay, so let us next see this lemma 654. So this is that lemma that we were talking about when we first started proving our main result. So we already know what this subspace V1 of V is. So let's not again repeat that. Instead, let's see what this lemma says. This lemma claims that our original vector space V has a subspace W which is invariant under T and such that V is the direct sum of that subspace V1 which we already have encountered and this W. So let's now see the proof. The proof starts by considering a subspace W with two properties, a subspace of V with two properties. These are the two properties. Let W be a subspace of V of largest possible dimension such that the following two conditions are true. Number one, W intersects V1 trivially. That is, their intersection has only the zero vector. And number two, W is invariant under T, under our operator T, original nilpotent operator. Now immediately a question arises. How do we know that such a W even exists? What is the guarantee that you can choose such a W? That must be answered first, because we cannot just simply choose something without knowing whether it exists or not. We have to, in fact, at least for our own sake, make sure that such a W exists. But how? I mean, why would such a subspace W exist? Let's again see what W is. First of all, W is a subspace of V. Okay. Let us just not consider this largest possible dimension for the time being. Let us simply think of W as a subspace of V that has these two properties. The first one is that W intersects V1 trivially, and the second one is that W is invariant under T. Whether such a subspace can be found, that's the first thing. Forget about maximal dimension. Yes, that can be found. You see, note that the zero subspace is a subspace of V such that it intersects V1 trivially, and this is also invariant under T. Why? Well, this intersection, of course, is easy to see why it is the trivial space 0. And what about the zero space being invariant under T? Well, the only vector in the zero space is the zero vector. And when you apply T on the zero vector, you again get the zero vector, which of course is here again, and that is why it is also invariant under T. So, the set, say, let me call it A, okay. We want to be absolutely sure about how exactly this W exists, okay. That's why I am writing these things. So the set A of all subspaces of V that, let me write the language itself, I mean in words, that are invariant under T and intersect V1 trivially, which mathematically means this, okay, is non-empty. Because the zero space is an element in A. Alright. Now let's collect the dimensions of the elements in A. The elements in A, after all, are subspaces of V, and that's why each one of them will have some dimension. Since V itself is finite dimensional, the set B of the dimensions of the elements in A is a non-empty finite set non-empty. We understand why it is non-empty, because A itself is non-empty. But why is it finite? Well, that's because every element in A is, after all, a subspace of V, and V is finite dimensional, means it has a dimension that is a non-negative integer, and all the dimensions of the elements in A need to be less than or equal to that dimension, because they are subspaces of V, and that's why there are at most finitely many choices. And so the set of these dimensions, which we are calling B, is finite, and that's why there will be a largest dimension, and corresponding to that dimension there will be at least one subspace in A, an element in A, which will have that dimension. So that's why choose a W in A such that dimension of W is the largest element in B. That's how we can know, that is, we know that W exists. A finite set of non-negative integers always has a largest element. Is the largest element in B. Okay, so now we know that such a W will exist. Maybe there are more W's, but we need only one. Alright, so what are the properties? Let me again write it here. What are the properties of W? W intersects V1 trivially, and W is invariant under T. So the original statement of the lemma seeks a subspace that is invariant under T, so that we already have for W. Also, we have the fact that W intersects V1 trivially. But what do we want to show? We want to show that our original space V is the direct sum of V1 and W. So one part of being a direct sum is already available here. The other part is that we need to now show that V is equal to the sum of V1 and W. So that's what we want to now show. Now, we want to show this. Suppose this is not true. That means V is larger than this sum. See, this sum anyway is a subspace of V because V1 and W both are subspaces of V. So, this sum not being equal to V means there is something else in V other than what we have in this sum. So, that is why you choose an element, a vector Z in V such that Z does not belong to V1 plus W. Alright, let us now recall that our operator T is nilpotent of index n1. That means this n1th power of T is the 0 operator. So with that, we next get this. Since, okay, now if you apply that on this vector Z, then what do you get? You get 0, which of course belongs to V1 plus W. So although Z itself is not in V1 plus W, when we apply this power of T on Z, then that result belongs to V1 plus W. Now this N1 may not be the smallest positive integer for which this is true. Maybe some smaller positive integer in place of N1 also makes this true. Says that T to the power K, I am not saying it should be 0, but it belongs to V1 plus W. So such a smallest K can be found because at least one N1 exists, and you know the well ordering property of positive integers. So that is why a smallest such exponent will exist. That is why we started with since. So we have to continue. There exists an integer K such that K is positive and less than or equal to N1. Okay, so this is first thing. Then the image of Z under T to the power K belongs to V1 plus W, and any lower exponent doesn't give us a vector in V1 plus W for all I less than k. Okay, so that just shows that k is the least positive integer for which these things happen, for which this happens, and no lower I can make that same thing happen. Alright. Now let's concentrate on this, because this vector after all is in V1 plus W, so it will be equal to some vector in V1 plus some vector in W. So let's just consider that. Now say this is equal to U plus W, where U belongs to V1 and W belongs to W. Okay. All right. Now let us after this what do we do? After this we use the fact that we again go back to this fact that the n1 power of t, when you apply on z you get 0, but with this new information. Now we start our calculation with 0. Okay, so 0 is this, which is just this. However, this can be written as the t to the power k image of z, and outside we have this operator n1 minus k, which makes sense because k is actually less than or equal to n1. So n1 minus k is a non-negative integer. So this power makes sense. Oh, and be careful, you cannot simply take any exponent, I mean any integer. If you are taking a negative integer here, that may not make any sense. That's because it will then indicate that the power you are considering involves inverse of t, which may not exist. Okay, t may not be an invertible or regular operator. But here there is no problem because n1 minus k is a non-negative integer. Now you use this expression for zt to the power k. What will you get? So this is u plus w n1 minus k. Because t is a linear operator, it will get distributed over the sum. ut to the power n1 minus k plus w t to the power n1 minus k. Considering that we started with 0, we get this, which implies that this is equal to minus w t to the power n1 minus k. Alright, let us now recall something that we have already established about the subspace V1. Remember, when we constructed V1, then we verified that V1 is invariant under T, just like W. I mean, the choice of W is such that its definition itself involves invariance under T. So W is invariant under T, and V1 is also, from our previous discussion, is invariant under T. Now V1 is, let's write together, V1 and W are both invariant under T. So since U belongs to V1, our vector U comes from V1, this again belongs to V1. Also, since W belongs to W, this also belongs to W. I mean, invariance of these subspaces under T means if you take any vector from any of these subspaces, it does not matter how many times you apply T on that vector. Here, for example, we have applied it n1 minus k times. The result, ultimate result is going to be in that subspace itself. That is invariance. Okay, so now what do we see? We see that this vector belongs to V1, and we see that this vector also belongs to W. So its negative also belongs to W. However, these two vectors are actually equal. So that thing belongs to both V1 and W. Hence, and so it belongs to their intersection, V1 intersection W. Hence, U T to the power n1 minus k equal to minus W n1 minus k, let me write like this, belongs to V1 intersection W, which however we already know from how W has been defined is the zero space, and that is why both of them have to be equal to 0. This implies, now we are not really interested in this, but this is equal to 0. This implies U T to the power n1 minus k is equal to 0. Now this is the point where we have to go back to the lemma that we proved in the previous video, and that lemma is oh, I hope I have written the lemma number, otherwise, I mean, you do understand what I am talking about, but do I have the lemma? Yes, 653 by lemma 653. If you go back to the statement of this lemma, you will see that this is precisely the condition under which we can say something about U, and that something is this. U is equal to U naught T to the power k for some vector U naught in V1. Okay. All right. So now if you go back to the original zt to the power k expression and use this fact that U looks like this, hence what was it? Zt to the power k is U plus W. So now U is this, U naught T to the power k plus W. Okay, so now we are going to do what? Now using this vector z and u naught, we will define another vector z1 as their difference. All these steps seem so haphazard and out of the blue. Well, they are. I mean, we do not really see what to do, why we are doing these things, but it will become clear ultimately when we get a contradiction. It's very difficult to say how one comes up with these steps. It's mainly trial and error, not blindly, of course. I mean, the people who work with these things for a long time, they have some things in their minds. They feel that this avenue will give me something. There is no guarantee. They go this way, that way, and some ways just make things fall in place, and ultimately we have a proof. Okay, so now consider this vector. Here, of course, it's a desperate attempt to get something wrong because it's a contradiction proof, right? So next we are considering this vector. Z1 is Z minus U. U naught, sorry. Yeah. Now, what can we do with this vector Z1? Well, the first thing we are going to do is this. What happens when we apply t to the power k on Z1? Of course, whatever we are going to get will come from this equation. Note that Z1 t to the power k is this, so this is Z t to the power k minus u naught t to the power k, which from this equation is equal to w. And this belongs to w, of course. All right. Now, since w is invariant under t, this means that if you do not stop here, so what have we shown? We have shown that the t to the power k image of Z1 is in W. If you do not stop applying t on this thing at this stage itself and you keep on going, okay. If you apply t once more, you will get that the t to the power k plus 1th image of Z1 is also in W. And that is happening because W is invariant under t, and you can go on and on as many times as you want. So that's why in general this belongs to W for all integers m greater than or equal to k. Okay, so far whatever we have done has been, it has come from this fact, right? That this belongs to V1 plus W. From this fact, we have got all these things. But what about that other thing which came with this condition? That no lower power of t makes z fall in this. That is, z t to the power I is not in this sum if I is less than k. We are also going to get something from that. The author writes, on the other hand, if I is less than k. If I is less than k, then set t to the power I does not belong to v1 plus w. We already know this. Okay. Now suppose z1 t to the power I, z1 is of course about this z1, belongs to w. Okay, this is w, this is not v1 plus w. Let's see what happens if we take this. Then clearly this also belongs to v1 plus w, because w after all is a subspace of v1 plus w. v1 is also a subspace of v1 plus w. But we already have, this is our supposition, okay. This thing that we are getting is a consequence of our supposition, but something that really already happens, which is true, is also this, that if you apply t to the power I on u, u naught. Okay, let me take u naught because otherwise I won't get the, yeah. So we have this thing belonging to v1. How? Well, that's because v1 is invariant under t, and this u naught, if you remember, comes from v1. So on u naught we apply t I times. No matter how many times we apply, the result is going to lie in v1, and hence u naught t to the power I also of course belongs to v1 plus w. But then you combine this one and this one, you will then get this z t to the power I. So what is z in terms of z1 and u naught? It is just z1 plus u naught. Why? Because z1 is z minus u naught, that's why. So this will become what? z1 t to the power I plus u naught t to the power I, and these things both belong to v1 plus w, and that is why this also belongs to v1 plus w. But that cannot happen. Why? Because of this. Okay, so that is why this supposition is wrong. Hence, the last supposition is wrong, i.e. z1 t to the power I does not belong to w. Alright. So this is one paragraph. After that, a new paragraph starts in which we use this vector z1 and the subspace w to generate a new subspace of V. And we name that new subspace W1. let W1 be the subspace. Well, in vector space we do not say generate, normally we say span. W1 be the subspace of V spanned by W and these vectors. And these vectors z1, z1t, z1t square and so on up to z1 t to the power k minus 1. Remember that k is a positive integer, so k minus 1 is not negative, it is non-negative. Okay, so it makes sense. All right. Now the first thing we are going to note about this subspace W1 is that Z1 itself does not belong to W1. But why? Yeah, I am also kind of a bit confused here as to why this is true. I thought about an argument, but is that really working? Suddenly I am just thinking that it may not work. Okay, let me just start because anyway it's there, no? Let's see what we can do. Since Z1 does not belong to W1. Oh, sorry. Oh, my statement was a little wrong. It's not that Z1 is not in W1, Z1 is not in W. But why? Let me try like this, as otherwise Z1 belongs to W. And so what is Z1, by the way? Z1 is nothing but Z minus U naught it was. This belongs to W. Okay. Shall I get something from here? And this implies oh yes, you see, because Z minus U naught belongs to W, so does it not say that Z belongs to W plus V1? How, you ask? Well, this is how. You just take something here, okay, just name it something else. Say you call it small w prime, like this. Say Z minus U naught is equal to W prime, but this W prime belongs to W. Then this implies that Z is equal to W prime plus U naught. W prime of course belongs to W, and this U naught is coming from V1. So that is why this thing belongs to W plus V1. However, that's not possible. Why? Because do you remember that in the beginning of the proof we considered Z to be a vector in V which is not in this sum. That is why it's not possible. And that is why Z1 does not belong to W. Oh yes, okay, so this is the thing. Since Z1 does not belong to W and W1 contains W, Oh, and if you are a little confused about this W1 being spanned by a subspace and then some other vectors, it is just this. You take the union of the set. W is after all a set also, no, a set of vectors. You take the union of W with the set of these vectors, then you get a set. So W1 is the subspace of V spanned by that set. And that is why W1 also contains W as a subset. So because of these two things, dimension of W1 is greater than dimension of W. Does it make sense? You see, because of this containment, W is a subspace of W1, so automatically the dimension of W will be less than or equal to the dimension of W1. That possibility of equality is still there. Simply from this containment, we cannot say that they are not equal. However, at the same time, there is an extra vector Z1 in W1 which is not in W. And that is why they are not equal. And two vector spaces which are related like this, there is a containment where the containment is strict, they cannot have the same dimension. From the theory of dimensions, we know that then the dimension of the larger one has to be strictly greater than the dimension of W. Okay. All right. Now, also, W1 is invariant under T. Let's see how. Oh, I erased this part. Okay, we can recall it when we need it. We are going to need the last line of the previous paragraph towards the end of this proof. Now, W1 is invariant under T. But how? Let's just understand that. How does a general vector look like in W1? Because W1 is being spanned by W and those vectors, a general vector is going to look like this. W plus, say, something, say beta naught Z1 plus beta 1 Z1 T plus beta 2 Z1 T square and so on, beta K minus 1, this, where this W is coming from W and these betas are all scalars. Alright. Now on this vector, if you apply T, what are you going to get? Of course, you will apply T on all these terms in the sum. When you apply T on W, the result you get will again be in W. Why? Because W is already invariant under T. That comes from the definition of W itself. What do you get when you apply T on this? You just get Z1T, beta naught Z1T. Then in the next term you get beta 1 Z1T square. So you are not actually leaving this set, or you are not leaving W1, because these vectors along with your W span W1. So you go on applying T on every term, you are going to get again something. I mean, especially in this part, you are going to get again vectors from here, except the last term. What happens to the last term? Well, the last term is going to be this. Right? And what can you say about this? It's obvious. If you go back and see what this thing is, then you will understand why ultimately this thing also belongs to W1. In other words, the T image of this entire thing, which is a general vector in W1, so this part I am leaving to you. Okay, what about this term? So once you convince yourself that this term also belongs to W1, you then see that on any vector from W1, if you apply T, the result is again in W1. And that is why W1 is also invariant under T. Okay, so what have we now got? We have got a new subspace of V, which we are calling W1. With what properties? One thing is that W1 is invariant under T. And the second thing is that dimension of W1 is greater than the dimension of W. Now it's time to think about the intersection of W1 and V1. If you have this, will something go wrong? Yes, something will go wrong. If you go back to the definition of W, what is W? W, besides being a subspace of V that is invariant under T and which intersects V1 trivially, also is such a subspace of highest possible dimension. Now, if W1 already is invariant under T, now if W1 also intersects V1 trivially, then that maximality of dimension is violated here because of this inequality. And that is why this cannot happen. Okay, due to that maximality. So let me continue from here itself. Because of the maximality of dimension of W, we must have W1 intersection V1 non-trivial. So there exists at least one non-zero vector in this intersection. Because that vector is going to lie in W1 also, so we can write this next. Hence, there exists a vector of the form this. W naught plus alpha 1 Z1 plus alpha 2 Z1 T plus, let me write one more term also, alpha 3 Z1 T square plus alpha K Z1 T to the power K minus 1. Why do we have K here? Because the suffix is one more than the exponent of T. So such a vector is how a general vector is going to look like if it is coming from W1. Now that vector needs to be non-zero. So let's mention that. This is how a general vector, non-zero vector in W1 looks like. Is also in V1. Is how did we start the sentence? There exists a vector, this in V1, where W naught is coming from W. Now the next thing we notice about this vector is that, and of course if you want you can say and where this belongs to W and the alpha i's are scalars, but that's understood from context. What else will they be if not scalars? Now we are going to next claim that all the alphas cannot be 0. If all the alpha i's are 0, then the non-zero, the vector of course needs to be non-zero, but then it just simply becomes W naught. And this W naught is in V1, but at the same time it's also of course in W. And remembering how this intersection is, this is 0. And this obviously is not possible because this is non-zero and this has only 0. So all the alpha i's can't be 0. Now if you look at the list of alpha i's, you start from alpha 1 and then go down the list. Maybe alpha 1 itself is non-zero, who knows? But you may encounter some zeros first, and then you may get a first non-zero alpha. So let alpha s be the first non-zero alpha. Ideally we should write alpha suffix I, but we can be a little not so rigorous in this way, not with the mathematics but with the language a little bit. Alright, which means what? It means that if one starts looking at these terms, alpha 1, z1 and so on, the terms which appear before the one which has this alpha s are going to vanish because those alphas are 0. So that means this sum will be simplified to some extent and we can write it like this. Hence, W naught plus z1 t to the power s minus 1 alpha s plus alpha s plus 1 t have to go to that part, do not have enough space. Plus alpha k t to the power k, because we have written s minus 1, that means we have taken that first. We have taken this operator, the s minus 1 power of t, as a common term outside of the actual sum. You see, instead of writing this sum, this part of the sum, forgetting W naught, Instead of writing the sum like this, you can write it also like this. On the single vector z1, you are applying alpha 1 plus alpha 2 t plus alpha 3 t square and so on up to alpha k t to the power k minus 1. And from that sum of operators, you can take t to the power s minus 1 common out. When you do that, you will have here k minus s. Okay, and this thing is a non-zero vector, and it's no need to write non-zero again. The more important thing is that it belongs to V1. Okay, so this is where we now stand. Now, do you remember a result that we proved, which was very easy to prove, about nilpotent operators? That if you look at a linear combination of powers of a nilpotent operator, our T is nilpotent, do not forget that. Okay. And if the first coefficient is non-zero, then that linear combination is invertible. I mean, after all, this linear combination is also an operator, and it is invertible or regular. And that thing is lemma 652. If you go back to that statement, you will see. Now, since alpha s is not equal to 0, the operator is invertible. And not just that, and its inverse, let's call that inverse R. You can call it anything you want. The author has called it R. And its inverse R is a polynomial in T. Yeah, this is the best type of form that an inverse can have. It's again a polynomial in T. And this has its own consequence. What is the consequence? It is that, you see, we know that V1 is invariant under T. Now, V1 will also be invariant under R. Why? Because R is after all nothing but a polynomial in T. Whether you apply single T on any vector from V1 or a polynomial in T, which may involve higher powers of T than this simple T, on that vector, again the result is going to lie in V1 itself, due to the simple fact that V1 is invariant under T. And that is why V1 is also invariant under R. And because of a similar reason, W1 is also invariant under R, because originally we proved along the way that W1 is invariant under T. And all these things are happening because R is a polynomial in T. So we just simply write, so both W1 and V1 are invariant under R. So, because of this fact that R is a polynomial in T. Now, let us apply R on this vector, which we have written here, which belongs to V1. What shall we get? if we apply R on this vector, then of course R will be applied on W naught. Plus, and then R will be applied on this entire thing. Now, R is the inverse of this. So, this and R will get cancelled and we will be left with only Z1 T to the power S minus 1. Now, this will belong to what? Because we are applying R on a vector from V1, so the result will lie in the R image of V1. That is, this belongs to V1 R. But because V1 is invariant under R, this is contained in V1. Oh, we however wrote here that W1 is invariant under R. Do we really need that or do we need W? Oh, okay. We are going to need W only. No need to write that W1 is invariant under R. Invariance of W1 under R was a consequence that came later. But initially, we already knew from the very beginning that W is invariant under T. Okay. And that's why W is also invariant under R, because of this fact that R is a polynomial in T. And that's what we need here actually. Alright. Hence, Z1 T to the power S minus 1 belongs to V1 plus WR. Okay, do you see what we have got here? I mean, how we are getting this here? That's because if you take again same argument, this is a vector in V1. So let us name this something. Say we call this V1. Okay, then that will imply what? Z1 T to the power S minus 1 is equal to V1 minus W naught R. Now V1 belongs to V1 and minus W naught R belongs to WR. That is why. Now if we continue writing our thing, and this thing is itself contained in V1 plus W. Alright. However, yeah, I think, okay. I messed up a little. You remember that in the last line of the first paragraph, we proved this, no? Z T to the power I does not belong to W. Actually, it should be this. Because otherwise, now what I am going to get from here, that won't help me. Do you remember how we showed this? By assuming that this thing belongs to W. That is, by assuming this. We assume that this thing belongs to W. That's how we started our proof in that last part of the first paragraph. Do not start from here. You start from here itself, because this is what we needed ultimately. No. After assuming that this belongs to W, we then wrote that this belongs to, as a result, W plus V1. You start from this itself, so that when you get a contradiction, you can write that is why this does not belong to W plus V1. In fact, instead of just simply telling you to do this, let me go back and do it actually. Yeah, why keep gaps? It's a mistake. I have to rectify it. How did we start that part? Let me start like that itself. On the other hand, set t to the power I does not belong to W plus V1 for that I less than k. Suppose Z1 t to the power I belongs to W plus V1. V1 plus W, same thing, okay. You can write W plus V1 also. Addition is commutative. Since we already have U naught t to the power I belongs to V1, so U naught t to the power I belongs to W plus V1 as well. But then Z t to the power I, which is Z1 t to the power I plus U naught t to the power I, also has to belong to W plus V1. And that is not the case. And that is why this supposition is wrong. And that's why we must have this. Z1 t to the power I does not belong to W plus V1. So you see that although everything is similar, whatever we did there, it was a little mistake on my part. Everything is similar. In spite of that, it really affects how we started. Here we started with a slightly different thing. So that supposition is wrong. You cannot start like that and then say that this is the case. But anyway, now we have this, and this is what is going to give us something wrong now. Okay. But something has gone wrong. What is it? You see, what have we got here? That this vector belongs to V1 plus W. Here, however, we see that this vector cannot belong to V1 plus W if I is less than k. In place of I, here we have S minus 1. Is S minus 1 less than k? What is S, by the way? Where is S coming from? You remember those coefficients? Alpha S came from here. So obviously S is less than or equal to k, but S minus 1 is less than S, strictly less than S, and that's why S minus 1 needs to be less than k. But then this one directly contradicts this. So let's just write this systematically. Since s minus 1 is less than k. This, however, is impossible. So we are now at a dead end. There is nowhere else to go. The only thing to do now is to go back and claim that because of this thing that we cannot go anywhere else. The very first supposition that we made must itself be wrong. Hence, the initial supposition must be wrong. That is, we must have V equal to V1 plus W. V1 plus W cannot be a proper subspace of V. It has to be equal to V, because the existence of that vector Z, in fact, that is the source of all the problems. And that's why we must have this. And this is what we wanted to show, because we already have the fact that V1 and W intersect trivially. Since this, we thus have the fact that V is the direct sum of V1 and W. And of course, in the definition of W itself, we have the fact that W is invariant under T. And that completes the proof of this lemma. Now, you may remember that in the original proof of our main result, we have already used V1 to get one diagonal block of that entire matrix of T. And that diagonal block turned out to be M in 1. Now, this is the fact that will let you do the induction step. I mean, you have got one block M in 1. Now you are going to get the other blocks also, and they are going to come from this part, W. That, however, we won't see today. And then the proof continues. It's not really very long after this. Only a few things are there. But we will see that in the next linear algebra video, next Saturday. So that's just it for tonight. And tomorrow we have our usual analysis. We have already proved that if we have two Riemann integrable functions f and g, then their maximum is also a Riemann integrable function. Tomorrow I think we are going to consider their product. The product of two Riemann integrable functions is also Riemann integrable. This we are going to see, and we will prove it also, or at least we will start the proof. So let's see that tomorrow. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.